Okay, so this is joint work with Duyal Yolcu. He's somewhere in the audience. Can't see him. Okay, but yeah. And also I would also like to thank the organizers for this really wonderful conference. I think it was a real success. So one thing, okay, when you just step off the train, I don't know how about you, but when the first thing you see is a quantum building, then you should know, I think there should be a success, and this is a success. So, okay, but returning to the talk, so there are two main points I want to talk about. So the first one is to define quantum Las Vegas complexity. So that's actually something that could have been done like 20 years ago, but wasn't done. Okay, and the second point of agenda is to show how it's very closely connected to the adversary bound, which is a well-known notion in quantum query complexity. Okay, so let's start with the Las Vegas complexity. So, and let's talk about the complexities in general. Okay, and when we're talking about quantum, we tend to draw inspiration from randomized computation. Okay, and so there is a casino in Gent, okay, but it doesn't seem to be doing very well that now. Okay, but okay, when we're talking about the algorithms, there are two other cities that come to mind. Okay, so these are Monte Carlo and Las Vegas. Okay, and so Monte Carlo and Las Vegas are two different models of randomized computation, and I am mostly focused on query computation, so I will be talking about Monte Carlo query complexity and Las Vegas query complexity. So the difference, okay, so the difference between Monte Carlo and Las Vegas. So in the Monte Carlo algorithm, so if we want to avoid some function, for instance, you have fixed number of queries, so you have a fixed budget. Okay, but you can be sloppy, so you can answer an answer that is not correct with some small probability epsilon. Okay, for Las Vegas, it's kind of differently. So you can't be sloppy, so you have to give the correct answer, but you can violate the deadline, so you can turn in your solution weight. And so what is your complexity is the expected number of queries you solve. So because it's a randomized algorithm for different executions, you can have different number of queries, so what's count is the expected number of queries. Okay, and I would argue that kind of Las Vegas is a bit nicer notion than Monte Carlo. Okay, in the following way, so there are 3 points I can mention why it is nicer. So it's kind of well defined because there is no dependence on epsilon. Okay, and for Monte Carlo, okay, there is a dependence on epsilon. So usually epsilon is 1/3. So we can talk about, okay, 1/3 error algorithms. Okay, but okay, 1/3 is an arbitrary constant. Okay, if you change this 1/3, you change complexity. And actually, Monte Carlo complexity is defined only after a constant factor. Okay, the second thing good about Las Vegas complexity, it was composes. Okay, because there is no need for error reduction. Yeah, so the complexity of the composed algorithm is just the product of the complexities of these constituents. Okay, and the third thing that Las Vegas complexity can be turned into Monte Carlo if you want. So you just, it's well known that if you have worst case L, so you can get L over epsilon Monte Carlo algorithm just by running that for that many queries, and then if the algorithm still hasn't ended, then you just terminate it by first and give out some output, doesn't matter what. Okay, and so by Markov's inequality, it holds that it's a good Monte Carlo algorithm. Okay, so quantum query algorithms are pretty much Monte Carlo. Okay, so you have a fixed number of queries, and you can give an error. Okay, but can we define quantum Las Vegas complexity? Okay, and more precisely, I would like to understand whether you can define Las Vegas complexity that has all these nice properties that I listed before. So well-defined, well-composed, can be turned into Monte Carlo if you wish. Okay, and so there are few related notions. I'm sure that this is not an exhaustive list. So zero-error quantum algorithms, they are actually 20 years ago, defined by Burman, Cliff, de Wolf, and Zalka. So this is a complexity notion, but it doesn't satisfy this nice property. So I don't have time to actually explain what it is, and so why it doesn't satisfy all these nice things. Okay, there's also variable time model by Ambani, so variable time input to amplification, variable time search. Okay, but it was not studied as a complexity measure per se. So it's not also, we're not talking much about this. Okay, so now I'm going to define Las Vegas complexity. Okay, and first, I want to recap what a quantum query algorithm is. So, as you learn in basic quantum computers algorithms class, so something like Grover's algorithms or Simon's algorithms kind of looks like this. So it's usually written as a kind of diagram with wires. So I write it with matrices. Okay, so there is some unitaries and there are queries in between. So it alternates between unitaries and current queries. Okay, so it's kind of always some function, defines some domain. Okay, so OX is an input oracle, so you can get individual symbols of XI just by executing via this thing here. Okay, so UFIs are input independent unitaries. They actually constitute the algorithm because the oracle, the query is actually fixed. Okay, and after you measure, you get the value of the function. So that's the usual query algorithm. Okay, so what I don't really like about this thing, so I want to make some changes. So too much detail here. So you just want to write some function, you have some input, it's distributed over different registers. So a bit too much detail, and a good thing, actually, when you sometimes turn to a more general problem, it turns out to be much, much easier. So this is the case here as well, because you just strip all the details that are not necessary, just get to the core of the argument. So the first difference, the first change I'm going to make, okay, so just go to a state conversion problem. So now D, it used to be the domain, now it's just some set of labels. Okay, no structure there of input oracles OX, just now arbitrary unitaries. So they used to encode the input, now they're just arbitrary unitaries. Okay, on input X, the algorithm has to perform this transformation. So previously it had to map the initial state to the value of the function. Now it's just a tuple of states, so it has to map psi of x to tau of x. So psi of x is the initial state, tau of x is the final state. Okay, so this means that if you A of OX is actually all this thing here, so it goes from this direction to this direction. If we apply it to the psi x, so we get tau x. So this is the state conversion problem. It's a generalization of the thing I mentioned earlier. And so the second change, which usually is kind of implicit, but it's very important in my talk. So I also can allow to skip the query. So maybe in other terms, I can allow executing not just the input oracle, but a controlled input oracle. So I can have, so it's a direct sum of the input oracle tensored by some identity and also direct sum with some other identity. So there's some parts of the state that just are not affected by the oracle on the query. So it's usually used also in usual algorithms as well, but it's usually not stressed that well. Okay, so now let's move to complexity. Okay, so that's again the algorithm. I just use this or tilde, this is a query, so just to save some space. Okay, so again, this unitary as before. Okay, so I'm interested now in just to define this Adversary complexity. I am observing how the algorithm is performing, or how it's executed on particular choice of the input oracle O, so it goes in here, and particular initial state xi goes in here. So I just execute it. So just apply these unitary operations. Okay, and let psi tie, so it's psi1, psi tie capital. So tie capital is just the total number of queries. So, and let psi t be the state just before the t query. Okay, and so it's actually here. So, and now let me zoom in on this part. Okay, so I just open, okay, this oracle from the previous slide. Okay, and I put this type psi t here, and it kind of process here and goes on to become psi type plus 1. Okay, and so that's the same thing. So I break down this psi t into two parts. So psi t with a bullet, psi t with a circle. Okay, and so this is part that's processed by the oracle, and this is part that is not processed by the oracle, so that stays intact. So that's kind of skips the query. Okay, and so the observation again, so I see that only this psi t bullet gets processed by the query, and the part doesn't change. So it's kind of maybe fair just not to count this part as a query, so because it doesn't change. Okay, and so that's precisely what we do. So we define Las Vegas complexity, so it depends on the algorithm, on the empirical O that goes here, and on the initial state Xi. So we define it as a sum over T from all these guys that gets processed by the oracle, their norm squared. Okay, so if you recall, so norm of substate squared is kind of probability that you get this outcome when you measure. So you can think that this guy here is, you can think about it as a probability that you actually query something and not skipping the query. Okay, and so if you sum over all the queries, so you can see it as expected number of queries, similar to Las Vegas complexity. Okay, so it depends both again, so it depends on the empirical and depends on the initial state. Okay, so going back to the state conversion problem in defined few slides ago, so where we have to move psi x into tau x using this input oracle O of x. So the input is now, the complexity is input dependent, so it depends on x. So for each input we have a different complexity, so how it used to be in randomized case as well. So now I can define not only worst case complexity, I can define a thing called a complexity profile. So I just list all the complexities of the algorithm on each input. So it's a d-dimensional vector with real entries, positive real entries. Okay, and then I define feasible complexity space. So it's the kind of all complexity profiles you can obtain by different algorithms. Okay, because now I cannot say, okay, this algorithm is much better than this, because on some inputs one algorithm can be better, another inputs another algorithm can be better. So I just define the whole like a subspace of feasible complexity spaces. Okay, and yeah, a bit of discussion about this notion. So it's actually a very natural definition. I hope you agree. Okay, it also came with Stacy Jeffrey if you attended Stacy's talk on Monday. There was a similar notion of a query weight. So that's essentially the same thing. And another thing, it's this notion composes very nicely. So there is no error reduction needed because there is no error. Another thing, it captures kind of true complexity of the subroutine. So there is no maximum. So again, if you attended and remember Stacy's talk, so composition of Monte Carlo is kind of complicated, and now it is kind of better because okay, we just capture the true complex tokens. There is no maximums. Okay, if you remember that talk. So so in a way we approve query in a query world the results of Stacy's as well. So it follows from this. Okay, but now what is not query is convention to Monte Carlo, and because now it's just a theoretical notion, it's not clear how to actually get anything out of it, how nice it may be. And now, but to convert to a Monte Carlo algorithm actually can execute and get some output, we have to go through the adversary bound. Okay, and the adversary bound is a powerful tool to prove very complex total bound. So this is a non-inclusive, non-excessive list of some works on the adversary bound. Okay, and yeah, okay, and so this, I just recall the condition of the state conversion problem. So I have to map psi x into tie x for all x in D. Okay, and so all of x is input oracle, it goes from M to M. Okay, so that's the formulation of the adversary bound. So maybe it looks a bit scary. Okay, but wait for a minute. I'll just explain how it works in a few minutes. So why it is not scary at all, actually, and very natural. Okay, another thing you might ask, okay, what is this? I've seen adversary bound. It doesn't look at all like this. Okay, so again, don't worry. I don't have the time to explain this. It's just for this particular problem, state conversion. You can get like usual adversary for functional evaluation that you can have seen maybe. Then just a special case of this, but you have to work a bit. Just move some formulas and you obtain, just believe me, it works. Okay, and so now if we have this definition, yeah, we can do something similar which I did with the algorithms. So I can define the objective profile. Okay, so this is an optimization problem. Okay, and so there's some conditions. We'll go into them later. Okay, the objective profile is just thing. So it's a multi-objective optimization problem. It's just it's a feasible solution V of x that satisfies this constraint. Okay, so this is just the list of squared norms of these vectors V of x. So again, I'll talk later a bit what this V of x mean. In general, I just want to state the main result now. Okay, so the objective profile, this vector, and then I can again define feasible objective space, as I did previously, again, is a subspace of R to the D. Okay, and so this is just all the objective profiles when V varies over all feasible solutions of this optimization problem. Okay, and so now I can state the main result. So I defined feasible complexity space when I talked about the algorithms, and I just defined feasible objective space when I talked about the adversary optimization problem. Okay, they are both subsets of R to the D. Okay, and so maybe we can hope that they are equal. That would be nice. So we are almost there. Okay, so what we can show is actually that the feasible objective space is a topological closure of feasible complexity space. And actually, this topological closure is needed there. If without this thing, its result is false. Okay, and maybe in more lay terms, what does this mean, this topological closure? So it breaks down into two things, is a lower bound and an upper bound. Okay, and lower bound, this means that every algorithm, so if you take an algorithm, you can turn it into a feasible solution of the adversary bound. Okay, so this is usually called lower bound. And upper bound, if you take a feasible solution of the optimization problem, you want to turn it into an algorithm. Okay, and but now we have an algorithm whose complexity profile is arbitrarily close to the objective profile of the feasible solution. So we do not get it exactly like in this case, but we can get as close as we want. Okay, and so both the adversary problem and the algorithm, they solve the same state conversion problem. Okay, and the algorithms also are exact, so there is no error there. Okay, so the lower bound is like in Lietop state conversion paper that I mentioned on one of the previous slides. And what is new, and I would like to talk about, is this greater simplified upper bound construction. Okay, so and few things I also want to stress about this result. So first, it is tight. So previous of a state generation, it was kind of semi-tight. It was lower bound for exact and upper bound for approximate. So now it's tight. Now it's exactly tight. So this means it's not up to a constant as it used to be, but it's really exactly equal. And the third thing, it's for all input simultaneous, not just the worst case, as it used to be previously. Okay, so now in the remaining few minutes, I'll just want to explain the intuition behind the adversary bound and to give this proof of the upper bound. So, okay, so this is a reformulation of the adversary bound. So it's reoptimizing over these vectors Vx. Okay, and so we have this condition in the inner product's initial state, target state, and this thing here. So I can rewrite this thing like this. So just a basic algebra. Okay, and now take a look at this thing. So maybe just this is maybe one of the crucial things you should remember from the adversary bound. So this intuition, so this is a change in the inner product between the initial state and the target state. Okay, so this is like the change in the inner product we want to achieve. Okay, and what is this thing? So this Vx before applying the input oracle, and this is Vx after applying the input oracle. So this means if we plug in Vx to the input oracle, then we get precisely the change in the inner product we need to convert from psi x to tau x. Okay, so we're going from exactly the required change in the Gram matrix of psi to the Gram matrix of tau. Okay, and so this actually optimizes on the Las Vegas complexity of these queries. So Vx is a query to the input oracle, but without actually asking how this query is going to get there. So we are just, this is kind of relaxation. So we're asking, okay, what is the best vector to give to the input oracle to obtain the required change in the Gram matrix? Okay, so this essentially gives the lower bound. Okay, because this is a relaxation, so this means that every algorithm can be turned into this thing. Okay, and for the upper bound, okay, I want to somehow get this Vx into the query oracle. Okay, and how do I do this? So again, I can rewrite. So this is identity from the previous slide. I can just stick things around. So I can write it like this. Okay, and so this means there exists a unitary U that maps this direct sum into this direct sum. Okay, because the inner products are the same for all x and y. Okay, then there is a unitary that maps the corresponding vectors. Okay, and so this is unitary is crucial in the construction of the upper bound of the algorithm that's based on the feasible solution to the adversary optimization problem. Okay, so let me just write this unitary again. So for shortness, I will put this v prime x. So this is just oracle applied to v. Okay, so we want to convert psi x into tau x. So what we actually convert is psi x plus 1 over square root of t vx, where t is a large integer. We go to tau x plus the same thing. Okay, so not exactly what we wanted, but okay, maybe close enough. Okay, so that's the algorithm. And so I start with this state here, as I promised. Okay, so I can rewrite this like this. So these are t terms here. So in a way, you can think this is a tensor multiplication by a uniform superposition on a t qubit. So just t direct sums of this psi x. Okay, and so now the punchline. Okay, so I have this v of x here, 1 over square root of t. Okay, I am applying, I apply unitary to, apply the input oracle to this. Okay, I get v prime x, so v prime x by definition is the result of the application of the input oracle. Now I can apply this unitary. Okay, so psi x plus v prime x, I get tau x plus vx. So I apply this unitary, I get this thing. Oh, interestingly, I get this state back. Okay, I can move it to the next one. I can apply the input oracle. I can apply the unitary. Okay, I get vx back. So I move to the next one. Okay, I apply the unitary. Blah, blah, blah. I just converted everything. Okay, that's the whole algorithm. Okay, and so, okay, so I have converted this to this. I use t queries. On each I process this thing, as you can see. So the total Randomised complexity is t queries times the squared norm of what have been processed. So this is vx squared. So this is precise with the objective value. Okay, taking t large, so it doesn't depend on t, which is interesting, which is nice. Taking t large, I can get this thing very, very small. So I'm essentially mapping psi x to tau x. And I can make also the exact algorithm, but this requires a bit more work. So I am not talking about this now. I don't have time, obviously. Okay, but you can do it also exact. So this is a kind of approximate. Okay, and also you get Monte Carlo from this very easily. So, okay, so this is exactly the same thing. If I just plug in psi x instead of psi x plus 1 over square root of t vx, I get to the state type wow x, because which is like of distance from the target state 2 times this norm of this error term here. Okay, and this is less than epsilon if t is square of vx norm divided by 4 epsilon square, and this is optimal as shown by, as nicely communicated to me by Robin Kahari. Okay, so that's it. So for conclusion, we defined Randomised complexity. It's a very natural definition, has all the nice property. Okay, very strong tightness to the adversary bound. You can say actual adversary bound precise, so almost the same thing as Randomised complexity. And extremely simple upper bound construction that I was able to explain you without actually leaving anything behind. Okay, and so just to finish, so what else? So what I didn't talk about and what is in the paper, and maybe some open problems. So duality in lower bounds, multiple input oracles. You can have not just one input oracle, but many input oracles. So it's nice for composition, nice for trade-offs. Input oracles beyond unitary, so actually you can apply something which is like not unitary, still works. Output condition beyond state conversion, so you can just implement a unitary. That is nice if you want to execute it into some subroutine. Okay, for function evaluation, okay, you can get applied for Boolean functions. For general functions, it's an open problem. We only know up to a constant factor, just not precisely. One thing I didn't mention is unidirectionality between versus bidirectionality. Okay, and so another thing I didn't mention, it's very interesting that for this definition of Las Vegas, you can turn Monte Carlo algorithm for function evaluation into Las Vegas algorithm for function evaluation, which is contrary to the randomized case. Okay, thank you. Okay, and that's it.
Okay, it's working. Time for 1 or 2 questions. Yes.
Thank you for the talk. So in your construction that allows the skipping of queries, right? If I'm understanding correctly, you essentially have a construction that has a condition qubit that lets the state either change or not change according to the query. This strikes me as being a little different from classical Las Vegas algorithms, right, which actually allow you to save time complexity. You write down a shorter computation when you make fewer queries, whereas here you always have to write that unitary, right? It's just controlled. So do you find this to be a real concern? Is there some way around this with an alternative construction?
Oh yeah, actually that's an excellent question. So as I said, this is not really an algorithm you can execute. This is kind of a notion of complexity. Okay, and exactly so it doesn't, in that sense, it's not similar to the usual Las Vegas complexity. But as I said, you can turn it into Monte Carlo. You add a bit of error and just to get the algorithm. So you can just use all the stuff in the Las Vegas complexity, calculate all the Las Vegas complexity, and then turn it into a Monte Carlo algorithm. Okay, it's an open question whether you can really get a Las Vegas algorithm in the traditional sense, so we have expected number of queries, so it's open. Maybe it's possible in some sense, maybe not.
Okay, another question.
What is your new complexity measure on some of our favorite Boolean functions like and parity? Is it
Oh, as I said, it's equal to the adversary bound.
exactly equal? So and it'll be exactly root n.
Yeah, so I mean, you can also get these profiles and everything, okay, but okay, for the worst case, it's exactly equal, as I said, yes.
Thank you.
Okay, more question? Okay.
Thank you. Very nice talk. I was wondering, how does it compare to the normal definition that we had defined, the zero error query complexity? Because, like, classically, these two are really the same, and in your case, it's not. So, can you say where the difference is?
Oh, the difference is okay in the definition, I would say. Okay, so one thing you showed that that zero error algorithms they do not compose, and so ours compose nicely. Okay, and
that's
so
why they're not the same, yeah.
Yeah, so they are not the same. Okay, and actually, it's kind of I didn't look much into that. So can you reduce one to the other? So it's kind of you can just take a look and see whether it's possible. So it's just also an open question yet.
Thanks.
Okay, so let's stop here. Let's thanks again.